Welcome to The Explainer. Today, we're breaking down what I think is one of the absolute most fascinating concepts in all of network engineering, ring network topologies. We're going to trace the journey of the ring architecture, starting right from its core theoretical concepts all the way down to the actual physical hardware that powered enterprise data closets for decades. We have got some truly brilliant engineering to uncover here, so let's jump right in.
Now, to really grasp why this technology was even created in the first place, I want you to imagine a chaotic meeting room. Everyone is just shouting their brilliant ideas at the exact same time. And, well, what happens? Nobody hears anything, right? It's just a total collision of noise. But imagine introducing a talking stick. You can only speak if you're holding the stick. Suddenly, the chaos just vanishes. Everyone gets a turn, communication is perfectly orderly, and zero data is lost. In the networking world, that talking stick is a digital control frame called a token, and it's basically the beating heart of what we're unpacking today.
Okay, let's dive into this. Here's our roadmap for the explainer. 1. What is ring topology? 2. The token passing mechanism. 3. Dual ring and FDDI. 4. Connecting the ring with MSAUs. And finally, 5. Token ring versus Ethernet.
So, starting with Section 1, what is ring topology? Just the basics.
If you look at the broader family of network layouts, you've got your bus, tree, star, mesh, and sitting right there is the ring. Now, what really sets the ring apart from the others is its elegant simplicity. Every single device on the network connects to exactly 2 neighboring devices, one on its left and one on its right, so it literally forms a continuous closed loop.
Which brings us to the formal definition. A ring topology creates a circular data path, but the thing that makes it truly special is that it functions as an active topology. So data packets travel unidirectionally, meaning strictly in one direction, from node to node. Because every single computer or node on this ring actively receives the signal and retransmits it to its neighbor, every node is essentially acting as a repeater. This means a ring network is fantastic for long-distance communication. The signal just doesn't degrade as it travels along the cable because it gets refreshed at every single stop. But, just having a circle of computers doesn't solve that chaotic meeting room problem on its own. For that, we really need a set of rules.
That brings us to Section 2, the token passing mechanism, or digital control frames.
Let's look at how this actually builds a completely collision-free environment. Step 1. An empty control frame, that's our token, circulates freely around the ring at really high speeds. Usually we're talking between 4 and 16 megabits per second. Step 2. If a computer wants to send a message, it has to wait for that empty token to arrive. Once it does, boom, it grabs the token, packs it with its data, slaps on the destination MAC address, and sets its own ID. Moving to Step 3, this now filled token travels along the ring. Every node checks it. If it's not for them, they just pass it right along. But when it reaches the correct destination, the receiver copies the data out of the frame. Finally, in Step 4, the token travels all the way back around the ring to the original sender. The sender verifies the receiver actually got the message, empties the token, and passes it right back to the network so the next computer can take a turn. It's incredibly predictable and, as you can see, completely eliminates the chance of 2 computers talking over each other.
But, as beautifully orderly as this all sounds, it harbors a massive vulnerability. Because the standard ring is entirely unidirectional, and it completely depends on every single node actively passing the signal to the next one, it has a glaring single point of failure. If just one workstation shuts down, or say someone trips over a single cable and unplugs it, that's it. The token can't complete its journey. The entire network goes down. Plus, trying to add or remove a computer during the workday disrupts the ring, which made it a total nightmare for IT administrators to manage or troubleshoot. So, how on earth did network engineers fix this super fragile design? Well, the answer lies in our next section.
Section 3, Dual Ring and FDDI, built for redundancy.
Now, what's really interesting about this slide is the stark contrast between standard token ring and FDDI, which stands for Fiber Distributed Data Interface. While standard token ring relied on a single loop of copper wire, FDDI was built for high-speed, mission-critical backbone networks. We're talking upgrading the speed to a whopping 100 megabits per second using optical fiber. But the true genius here? The dual counter-rotating rings. It actually features a primary ring for normal data transmission and a secondary ring where data flows in the exact opposite direction. Under normal conditions, that secondary ring just sits completely idle, acting as a trusty standby backup.
And this is where the fault tolerance just gets incredibly clever. Let's say a cable gets cut on an FTDI network. A mechanism called ring wrapping instantly kicks in.
the devices on either side of the broken cable literally loop the primary ring back into the secondary ring, turning those dual rings into one giant, continuous, single ring. The network survives. But wait, what if a physical device actually loses power? Well, FTDI utilizes an optical bypass switch. If a computer shuts off, internal optical mirrors physically redirect the light signal right past the dead machine, completely maintaining the integrity of the ring. And for absolutely critical servers, FTDI allows for dual homing. That means the server connects to two separate concentrators. If the active link fails, the passive backup link instantly wakes up. I mean, it was just an absolute masterclass in network redundancy. Okay, so we've talked a lot about the theory, the tokens, the flow of light. But what did this actually look like in a real office? Let's ground this in some physical hardware.
Moving on to Section 4, connecting the ring with MSAUs, multi-station access units.
So MSAU stands for Multi-Station Access Unit. Sometimes IT folks just call it a MAU. This was a central piece of hardware that sat tucked away in the IT closet. You see, you didn't actually wire computers in a physical circle around the office floor. I mean, that would be a massive tripping hazard and a total management disaster. Instead, you plugged every single computer into the MSAU using its own separate cable, creating a star shape. But inside that MSAU box, the circuitry actually wired those connections into a logical ring.
And this really brilliantly illustrates the difference between physical and logical topology. Physically, your cables look like a star, which makes it super easy to manage from one central hub. But logically, the data is still strictly passing sequentially in a circle. This piece of hardware completely solved the scalability issue too. Let's say an MSAU had 8 ports. What happened when you hired your 9th employee? Well, MSAUs featured these special ports called RI, or ring in, and RO, ring out. You'd simply take a cable, plug it from the ring out port of the first MSAU right into the ring in port of a second MSAU. This expanded your logical ring across multiple hardware units, letting you scale your network seamlessly in multiples of 8. On top of that, the MSAU had the physical relays to actually bypass support if a computer was unplugged, preventing that dreaded single point of failure we talked about earlier. Yet despite all of this brilliant engineering, the deterministic tokens, the amazing fault tolerance, the clever MSAUs, ring topologies eventually lost the battle for the local area network.
Which brings us to our final segment, Section 5, Token Ring versus Ethernet, the LAN Wars.
So the crucial point is really understanding the philosophical difference between these two IEEE standards. Token ring, that's standard 802.5, was deterministic. It was this orderly, polite society where everyone waited their turn, native priority handling made sure important data went first, and collisions literally didn't exist. But it was highly complex to maintain. On the flip side, you had Ethernet, standard 802.3. Ethernet used a protocol called CSMA/CD. To put it simply, Ethernet was the chaotic meeting room. Any computer could shout whenever the line was quiet. If 2 shouted at once, they detected a collision, backed off for a random microsecond, and tried again. It was messy, it had 0 native priority, and under heavy loads, performance could really suffer.
But Ethernet had one massive, overriding advantage. It was up to 70% cheaper to install and manufacture. It used cheaper cables, simpler hardware, and honestly required way less specialized knowledge to set up. And while Token Ring was kind of just chugging along at 4 to 16 megabits per second, Ethernet rapidly evolved. It pushed to 10 megabits, then quickly to 100 megabits, completely blowing past standard Token Ring speeds. That combination of being dirt cheap and incredibly fast cemented Ethernet's absolute victory in the LAN wars, leaving Token Ring to quietly fade into computing history.
But the legacy of the ring didn't actually die. It just evolved. The core concepts of self-healing networks and automated failovers that were pioneered by FTDI, those are foundational to how we build resilient systems today. Which leaves us with a pretty fascinating question to ponder. As we build these incredibly complex, redundant cloud architectures across multiple physical data centers today, how much of that underlying philosophy of automated survival and active-passive backup links is directly inherited from those brilliant engineers who first figured out how to wrap a broken optical fiber ring? The hardware definitely changes, but the lessons of fault tolerance, those are permanent. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you in the next one.